solutions to these bar charts. They are solved as a PDF, but I want to go through part 2 at least as well. I know we did part 1 in class. I'm going to try to do part 2 in class before we have our test, but want to make sure that these are available. At any rate, so I'm going to skip part 1, go to part 2, which is more mathematical. And this is asking you to calculate some things. So number 1, a cart moving 5 meters per second collides with a spring. The instant the cart's motionless, what's the largest amount the spring can be compressed? Assume no friction. So initially, it's got kinetic energy. At the end, it's got elastic energy. I'm basically giving you... oh, I didn't give you the system. I should have said that. So the system here would be cart, spring, earth. At any rate, I think about the idea here. I start off with an initial type of energy, end up with a final type of energy. Ke is equal to energy elastic at the end. So now if I want to figure out the compression of the spring, I'd say my kinetic energy is 1/2 mv squared. My elastic potential energy is 1/2 kx squared, or delta x squared. I've got every number except delta x, and that comes up to 2 meters. So EI initial equals E final. Super useful. So this now says a rocket shot straight up in the air with a slingshot had been stretched 0.30 meters. It starts at 0 position, you can see that, and it's got no air resistance. So one thing here I noticed is that this mass is in grams. It really should be in kilograms, so you're going to have to convert that. 500 grams is 0.5 kilograms. You should know how to do metric conversions. If not, there's some metric conversions on your formula sheet. So again, I'm going to look here, and I'm going to say this is at 0 position. I'm going to have initially elastic potential energy, at the end gravitational potential energy. So E initial equals E final. E elastic equals E grav. Elastic is 1/2 k delta x squared. Gravitational mgh. So I'm going to put all those in, and I get a h of height of 0.9 meters. For number 3, I've got Earth, coast, or surface as my system. It says that determine the speed or the velocity at the end here. 10% loss due to friction. You can see I screwed up here and had to erase. At any rate, so there is friction in this case. I'm going to include everything in here. So it basically just doesn't say that the energy leaves the system. It says that it's thermal energy or heat energy somewhere in the system, the car, the track, or something like that. So I have E initial is equal to E final plus the work done by friction. So I'm going to say E grav is equal to kinetic energy plus E thermal, or E internal. So I have mgh, and that's my initial energy. So when I multiply those, I get 2,000 joules initially. 10% of that is 200. So if I have 2,000 joules initially, I'm left with 1,800 joules. And so now that's going to equal the kinetic energy at the end. So I've got 1,800 is 1/2 mv squared. That comes out to 9.5 meters per second. If you had used 9.8 for this, your answer would be a little bit different. Kind of like for a lot of these, if you use 9.8 mathematically, your answer might be a little bit different. This last one I thought was kind of challenging. So it says the bullet strikes a block of wood, which exerts on average a force of 50,000 newtons to stop the motion of the bullet. How far does the bullet penetrate? Show your work in math below. So I'm going to have my system as bullet, earth, and block. So essentially here at the end, there's no kinetic energy. Here at the beginning, there is. I said the bullet was a little above the ground, so I gave it a little gravitational energy, but it's the same at the beginning and the end, and that won't affect my calculation. So this has kinetic energy at the beginning, and at the end it's got internal energy or thermal energy due to the fact that this force pushed into the block. So I have kinetic energy initially is going to equal the work done by friction to slow the block down. So I have 1/2 mv squared. Notice I'm using standard units of mass, that's kilograms. Meters per second is the standard unit of velocity. And then that's going to equal the force times the distance that's pushed in. So 50,000 times d end up getting, this is 0.031 meters. So this one might have been tough if you didn't recognize that it was work by the block on the bullet to stop it, and work as force times distance. I think this one should have been doable. You might have taken 10% off the speed instead of 10% off the energy. That would have been a mistake that would have been easy to do. This one should have been pretty straightforward. This one should have been pretty straightforward. So I hope that helps.